Section 1 Introduction. Over the past few years, we've seen incredible advancements in pre-trained large language models like GPT, BERT, and T5, which have brought together the fields of language, image, mesh, and multimodal modeling. However, a universal pre-trained model for human motion and language still hasn't emerged. The introduction of such a model, designed to handle a wide range of motion-related tasks, could significantly benefit various sectors, such as gaming, robotics, virtual assistants, and human behavior analysis. Earlier studies on human motion have investigated several tasks, including motion creation, motion captioning, and motion prediction. Some recent text-to-motion studies have tried to use pre-trained models relevant to language. For instance, the MDM model learns a motion diffusion model with conditional text tokens from CLIP, while MLD enhances the efficiency of the motion diffusion process by integrating motion latent space. Motion CLIP and TM2T, on the other hand, focus on modeling the intertwined relationship between motion and its text description. However, these approaches regard motion and language as separate entities and often require strictly paired motion and text data. Moreover, since these models are task-specific, they struggle to effectively generalize to unseen tasks or data due to their limited understanding of the relationship between motion and language. Our focus is on developing a pre-trained model that understands the correlation between motion and language, which can then be applied to a variety of tasks using a larger and more diverse dataset. There are two main challenges in pre-training a promising motion-language model. The first is modeling the relationship between language and motion, and the second is creating a uniform multitask framework that can be generalized to new tasks. Human motion, like human language, tends to have semantic links, which can be viewed as a kind of body language. Building on this insight, we draw from the Vision Language Pre-Training Model BATE-3 to consider human motion as a unique foreign language. By bringing together motion and language data and coding them within a single vocabulary, the relationship between motion and language becomes more clear. With the recent surge in larger-scale language data and models, pre-training a motion-language model holds great potential to enhance performance in motion tasks. Furthermore, this pre-training on language allows for textual instructions, making the model more adaptable and user-friendly for a variety of motion tasks. In this work, we introduce a uniform motion-language framework, which we've named MotionGPT. This framework leverages the robust language generation and zero-shot transfer abilities of pre-trained language models for human motion-related tasks. To equip MotionGPT with the capability to understand and produce human-like motions, we first create a motion vocabulary, using a motion-specific vector-quantized variational autoencoder (VQVAE) model, similar to an English vocabulary, and then turn raw motion data into a sequence of motion tokens. These tokens are then processed by a pre-trained language model that learns the underlying structure and rules of the motion language, along with its relationship with the corresponding textual descriptions. We devised a two-stage training scheme to effectively integrate language and motion in MotionGPT. First, the language model is pre-trained on the raw motion dataset to learn the basic structure and rules of the motion language. For prompt tuning, the language model is fine-tuned on an instruction dataset, which includes both textual descriptions and motion data, to learn the correlation between the two modalities. Our experiments show that MotionGPT performs exceptionally well in text-to-motion, motion-to-text, motion prediction, and motion in between tasks. To summarize our contributions, 1. We've proposed a uniform motion language pre-trained model, MotionGPT, which treats human motion as a foreign language, brings natural language models into motion-related generation, and performs various motion tasks with a single model. 2. They introduced a motion language training scheme with instruction tuning, which learns from task feedback and provides promising results through prompts. 3. We've created a general motion benchmark for multitask evaluation, where MotionGPT shows strong performance across various tasks, including text-to-motion, motion-to-text, motion prediction, and motion in between. All the codes and data related to these tasks are available. Section Summary. The paper discusses the need for a pre-trained motion language model that can support various motion-relevant tasks and benefit fields like gaming, robotics, virtual assistant, and human behavior analysis. The authors propose a uniform motion language framework called MotionGPT that treats human motion as a foreign language and integrates motion and language data within a single vocabulary. They also introduce a motion language training scheme with instruction tuning and achieve state-of-the-art performance on diverse motion tasks. Section 2 Related Work. Section 2 Related Work. Creating human-like motion using a range of inputs, like text, action, and partial motion, is the main goal of human motion synthesis. One of the most essential tasks in this field is text-to-motion generation, which allows for the creation of motion using user-friendly and convenient language inputs. Models like MDM, MLD, and T2MGPT have made substantial contributions to this area. MDM suggests a diffusion-based model which is trained on multiple motion tasks independently. MLD further refines the latent diffusion model to generate motions, taking different conditional inputs into account. T2MGPT, on the other hand, examines a generative framework that is based on a vector-quantized variational autoencoder, VQVAE, and the generative pre-trained transformer, GPT, for creating motion. Moreover, there's the motion completion task which deals with the generation of motion based on partial motions, creating intermediate motion while the start and end portions remain constant. Despite the promising outcomes shown by these methods for various human motion tasks, most of them struggle to use a single model to handle multiple tasks. To address this limitation, we suggest a unique approach that views human motion as a foreign language and capitalizes on the strong language generation and transfer capabilities of pre-trained language models. In the realm of human motion captioning, we use natural languages to describe human motion by learning the mapping from motions to language with the help of two statistical models. Recurrent networks have also played a crucial role in this process. A recent innovation in this area, TM2T, introduced a new way to represent motion that compresses motion into a brief sequence of discrete variables, then employs a neural translation network to build links between the two modalities. Although earlier research such as TM2T integrated captioning modules into their training pipeline for motion generation, these methods are limited to bidirectional translation between text and motion within one uniform framework. Large-scale language models, powered by extensive datasets and sizable model structures, have shown remarkable comprehension and generation capabilities, pushing natural language processing to the next level. BERT, for instance, pre-trains deep bidirectional language representations that aid various downstream tasks. Meanwhile, T5 offers a unified framework that transforms all text-based language problems into a text-to-text format. Further studies have shown that by fine-tuning pre-trained models using pairs of instructions and corresponding answers, the performance of these models can be enhanced. Flan demonstrated an instruction tuning technique that outperforms non-tuned models in unseen tasks. Multimodal models that can process text alongside other modalities such as images, audio, and videos have recently gained momentum. For example, CLIP learns a semantic latent representation that pairs images with corresponding language descriptions. Despite these strides, the creation of multimodal language models capable of handling human motion is still in its infancy. Current text-to-motion generation methods, which can be described as caption-to-motion, have their limitations. While they can create motion from text descriptions, they often struggle to handle user instructions in a context-specific way, such as MotionGPT does. In response to this, we suggest MotionGPT, a model that merges natural language models with human motion tasks effectively. This solution would provide a comprehensive answer to motion synthesis challenges. Section summary. Several methods have been proposed for generating human-like motion, including text-to-motion, motion completion, and motion captioning. However, these methods are limited in their ability to handle multiple tasks and provide context-specific instructions. To address this, the authors propose MotionGPT, which integrates natural language models with human motion tasks to provide a unified solution for motion synthesis problems. This approach leverages the strong language generation and zero-shot transfer abilities of pre-trained language models and aligns the latent space with a motion autoencoder. Section 3 Method. In our method section, we delve into the details of our proposed model, MotionGPT, which has been designed to incorporate significant language data and models into tasks involving motion generation. This new framework can be visualized as a combination of two primary components, a motion tokenizer and a motion-aware language model. Firstly, the motion tokenizer translates raw motion data into discrete motion tokens. The motion-aware language model, informed by large language pre-training models, then learns to comprehend these motion tokens, guided by accompanying textual descriptions. For motion-related tasks, we've implemented a three-stage training process for MotionGPT, focusing on the training of the motion tokenizer, motion language pre-training, and instruction tuning. Our motion tokenizer consists of two parts, a motion encoder and a motion decoder. It translates a sequence of M frames of motion into L motion tokens, and it can also convert these tokens back into the original motion. Here, each token represents a portion of the motion, with L being the factor by which the motion is divided into tokens. Once the model is given a sentence, of length n, that describes a motion-related question or demand, the goal of MotionGPT is to generate an appropriate answer in the form of L tokens. These tokens could represent either human motion or text, resulting in either a sequence of motion or a descriptive sentence related to the original motion. To convey motion in discrete tokens, we've pre-trained a 3D human motion tokenizer based on the Vector Quantized Variational Autoencoders (VQVAE) architecture. Like the general tokenizer mentioned above, our motion tokenizer also comprises an encoder and a decoder. The encoder is designed to generate discrete motion tokens packed with information, while the decoder can transform these tokens back into motion sequences. This approach allows us to present motion as if it were a language, making it easier to merge motion and language for various tasks. In more detail, the motion encoder applies 1D convolutions to frame-wise motion features along the time dimension. To obtain a set of latent vectors, we then transform these vectors into a set of codebook entries through a process called discrete quantization. Our learnable codebook is essentially a collection of k latent embedding vectors, each with a dimension of d. Quantization is the process where each latent vector is replaced with its closest codebook entry, effectively mapping these high-dimensional vectors to a finite set of symbols or tokens. The motion decoder then maps these tokens back into the raw motion space, recreating the motion with M frames. To train this motion tokenizer, we utilize three specific loss functions for training and optimization: the reconstruction loss, the embedding loss, and the commitment loss. To enhance the quality of the generated motion, we also employ techniques such as L1 smooth loss and velocity regularization in the reconstruction loss, as well as exponential moving average and codebook reset techniques to optimize the use of the codebook during training. More detailed information about the structure and training of our motion tokenizer can be found in the supplementary section. Section Summary. The MotionGPT framework is proposed to integrate large language data and models into motion generation tasks. It consists of a motion tokenizer that converts raw motion data into discrete motion tokens and a motion-aware language model that understands the motion tokens from language pre-training models. The three-stage training scheme of MotionGPT includes training the motion tokenizer, motion language pre-training, and instruction tuning. Section 3.2 Motion-Aware Language Model. In the section titled 3.2 Motion-Aware Language Model, we introduce a novel approach to integrate human motion and language in a unified model. This is made possible by our unique motion tokenizer, which translates a sequence of human movements into a series of motion tokens. This process allows us to represent human motion and language in a similar fashion, leading to a more cohesive and integrated model. To elaborate, each motion token in the series is given a unique index number, creating a sequence of indices. This methodology is akin to how previous language models, such as T5, handle text by encoding it into word piece tokens. However, where previous methods typically treated text and motion separately, we endeavor to unify them. Our goal is to model text and human motion together and consistently. To achieve this, we merge the original text vocabulary with the motion vocabulary, which aligns with our motion codebook. This combined vocabulary includes special tokens, which denote the start and end of the motion. Consequently, we have a comprehensive, single vocabulary that can represent a wide range of motion-related tasks, with both the input and output, words, originating from the same vocabulary. The words, in this context, can symbolize natural language, human motion, or even a blend of the two, based on the task at hand. Our model, named MotionGPT, is highly flexible. It can represent and generate a variety of motion-related outputs using a single model. For generation tasks, we use a transformer-based model that effectively maps input sequences to the output. Our input consists of a sequence of tokens, where each token is part of our unified vocabulary and the total number of tokens signifies the input length. Likewise, the output is also a series of tokens from the same vocabulary, with its length indicating the output length. The model operates in such a way that the input tokens are processed by the transformer encoder, and the decoder then predicts the likely next token at each step. This prediction process is performed in an autoregressive manner, i.e., each prediction depends on the previous ones. The ultimate aim during training is to maximize the log likelihood of the data distribution. By doing so, MotionGPT learns to recognize the underlying patterns and relationships within the data, which enables the accurate and meaningful generation of the target words. During the inference process, target tokens are sampled recursively from the predicted distribution until the end token is reached. This approach allows us to generate the target sequence in a step-by-step manner. Each token is determined based on the previously generated tokens and the given source input, allowing us to create outputs that are as close to the original sequence as possible. Section Summary. The motion-aware language model maps human motion to motion tokens and combines them with text word piece tokens to learn motion and language jointly. The unified text motion vocabulary allows for the flexible representation and generation of diverse motion-related outputs within a single model. The transformer-based model predicts the probability distribution of the potential next token at each step in an autoregressive manner, enabling the generation of the target sequence in a step-by-step manner. Section 3.3 Training Strategy. Our approach to training revolves around the transformation of T5 models, which have traditionally only been exposed to language data. Our goal is to bridge the gap between motion and language, allowing these models to understand human motion concepts. We accomplish this by introducing a motion vocabulary to the existing language model. This training process unfolds in 3 phases. 1. First, we teach the model to understand and represent human motion as discrete tokens, a process we refer to as training the motion tokenizer. By doing this, any sequence of human motions can be translated into a series of motion tokens, making it compatible with the textual information that the model is already familiar with. Once we've fine-tuned this process, we don't alter the motion tokenizer throughout the remaining stages. 2. In the second stage, we train the T5 models on natural language datasets, but with a twist. This time, the data is a mix of language and motion. We use both supervised and unsupervised techniques for this purpose. In the unsupervised training, a certain percentage of tokens in the input sequence are randomly replaced with a special marker. The target sequence is then created by extracting the missing spans of tokens, marked by the special tokens used in the input. Additionally, we learn the relation between motion and language using paired datasets of text and motion. This involves training our MotionGPT model on motion language translation, where the input is either a human motion or a text description. Our aim in this stage is to equip the model with a good understanding of the relationship between text and motion. 3. In the final stage, we fine-tune the model's ability to interpret instructions related to motion. This involves creating a text-motion dataset that we treat as instructions. We base this dataset on existing text-to-motion datasets like Human ML3D and KIT. We define 15 core motion tasks, such as generating a motion sequence from text, creating a caption for a motion, predicting a motion, and others. For each task, we provide numerous instruction templates, resulting in over 1,000 unique tasks, each with its own prompt. For instance, for a motion generation task, the instruction might be, can you generate a motion sequence that depicts a person emulating the motions of a waltz dance? For a motion captioning task, the prompt could be, provide an accurate caption describing the motion of less than motion underscore tokens greater than, where less than motion underscore tokens greater than is a sequence of motion tokens created by our motion tokenizer. Our results show that this kind of instruction tuning enhances the model's performance across a wide range of tasks and even improves performance on tasks it hasn't seen before. You can find additional examples of prompts in the supplementary material. Section Summary. The training strategy for our model includes 3 stages. 1. Training of motion tokenizer to represent human motion as discrete tokens. 2. Motion language pre-training stage to learn the relationship between motion and language using unsupervised and supervised objectives. And 3. Instruction tuning stage to tune the model based on prompt-based instructions for different motion-relevant tasks. We construct a multi-task text motion dataset by formulating it as instructions, resulting in more than 1,000 different tasks, each having a unique instruction prompt, which leads to improvement across various tasks and enhances the model performance for unseen tasks or prompts. Section 4 Experiments. Section 4 Experiments. Our work, MotionGPT, was put to the test through multiple tasks and datasets connected with motion. We'll discuss the specific settings of the datasets we used, how we measured our performance, and the fine points of our implementation. We'll start by showing how MotionGPT compares with other state-of-the-art approaches across an array of tasks. Then, we'll examine how it performed in particular comparisons on tasks like turning text into motion and vice versa, predicting motion, and creating motion in between. For a more in-depth look at our results, as well as user studies and further implementation specifics, refer to our supplemental material. Section 4.1. Experimental Setup Datasets. We're looking at a general motion synthesis that supports a range of task settings, so we've used a variety of previous datasets and modified benchmarks to assess MotionGPT. Our study mainly used 2 datasets for turning text into motion, Human ML3D and KIT. The KIT dataset provides over 6,000 textual descriptions matched with nearly 4,000 motion sequences, while the newer Human ML3D dataset has around 15,000 motion sequences from a mass and about 45,000 sequence-level text descriptions. To evaluate MotionGPT on tasks like predicting motion and completing motion, we use the motion sequences in the Human ML3D dataset, which is part of the larger AMAS dataset. To ensure a fair comparison, we used the same representation of motion as previous studies, combining joint velocities, positions, and rotations. This consistent representation helps future studies with MotionGPT. Evaluation metrics. We evaluated our model using 4 types of metrics. 1. For motion quality, we use the Frechet inception distance, FID, to measure the difference between the feature distributions of the generated and real motions. When completing motion, we used average displacement error, AID, and final displacement error, FDE, to evaluate how accurate the predicted motion was. 2. For generation diversity, we use the diversity, DIV, metric to assess the variance in the features extracted from the motions. Multimodality, M, measures how diverse the generated motions are from the same text description. 3. For text matching, we used a metric called motion retrieval precision, R precision, to evaluate the accuracy of the match between texts and motions. Multimodal distance, MDist, measures how close the motions and texts are. 4. For linguistic quality, we used natural language studies metrics like Blue, Rouge, Cider, and BERT score to evaluate the quality of the generated motion captions. Implementation details. Our motion tokenizer codebook, KIN, R, 512 x 512, was used for most of our comparisons. The motion encoder, E, uses a temporal downsampling rate of 4. Our language model is based on the T5 architecture, and our baseline model consists of 12 layers in both the encoder and decoder. The output size of our feed-forward networks is D_text FF equals 3072, and the attention mechanisms have an inner dimension of D_text KV equals 64. The other sub-layers and embeddings have a size of D_text model equals 768. We used the Atom W optimizer to train our models. We trained our motion tokenizers with a learning rate of 10⁻⁻⁴, and a mini batch size of 256, while our language models have a learning rate of 2 × 10⁻⁴ for pre-training and 10⁻⁴ for instruction tuning, with a mini batch size of 16 for both stages. The motion tokenizer was trained over 150,000 iterations, and the language model underwent 300,000 iterations during pre-training and another 300,000 during instruction tuning. All our models were trained on 8 Tesla V100 GPS. Section Summary. The performance of MotionGPTs is evaluated across various motion-relevant tasks and datasets, including text-to-motion, motion-to-text, motion prediction, and motion in between. The evaluation metrics include motion quality, generation diversity, text matching, and linguistic quality. The implementation details include the motion tokenizer codebook, motion encoder, language model, and optimizer used for training. Section 4.2 Comparisons on Motion-Relevant Tasks. Section 4.2 is entitled, Comparisons on Motion-Relevant Tasks, and it presents a thorough comparison of our model, MotionGPT, with other leading approaches in the field. The section is further broken down into comparisons on multiple tasks, text-to-motion, motion-to-text, and motion prediction and in-between tasks. In the first part, we discuss our work on various motion-related tasks, all viewed through a unique framework that considers human motion as a foreign language. We utilize the FLAN T5 base model, pre-trained on a substantial 220 million parameters, as our backbone. This model is then fine-tuned through a pre-training stage and instruction tuning phase for all subsequent comparisons. We stack MotionGPT against other cutting-edge methodologies in key tasks such as text-triggered motion generation, motion captioning, motion prediction, and motion in between. The results demonstrate that our MotionGPT holds its own in all evaluated tasks, showcasing its potential to manage a broad spectrum of motion tasks using a single model. The Comparisons on Text-to-Motion subsection centers on a task that involves creating human motion sequences from given text inputs. We use the pre-trained MotionGPT model and fine-tune it for the text-to-motion task. We measure our model's performance against other top models on the human ML3D and KIT datasets. Our results, with a 95% confidence level based on 20 repeated runs, show that MotionGPT is competitive in most of the measured metrics. The next subsection, Comparisons on Motion to Text, is about a task that generates a text description from a provided human motion sequence. We gauge the pre-trained MotionGPT's performance against the recent TM2T model on the human ML3D dataset. We also calculate the average number of words used in the text descriptions to compare results further. Please note that the evaluations consider pre-processed ground truth text, which disregards grammatical tense and the plural forms of words. In our study, we use the actual ground truth text descriptions for a more accurate evaluation. The comparison reveals that MotionGPT performs exceptionally well in generating text descriptions of given motions. The final subsection, Comparisons on Motion Prediction and in Between, presents a general evaluation of motion completion. Here, we utilize a section of the amassed dataset, a motion-only collection, to test the motion completion ability of MotionGPT. We give the first 20% of the motion sequence as conditions for the motion prediction task, and for in between, we mask about half the motion randomly for completion. We fine-tune MotionGPT specifically for this task and use FID, AID, and FDE as evaluation metrics. We also test MDM on motion prediction, using their provided model that also supports motion in between through a technique called masked motion in painting. Our results indicate that MotionGPT has the highest quality and diversity in motion completion. Section Summary. The authors introduce a framework that treats human motion as a foreign language, allowing for exploration of diverse motion-relevant tasks. They evaluate their MotionGPT model against state-of-the-art methods on tasks such as text-conditioned motion generation, motion captioning, motion prediction, and motion in between, achieving competitive performance across all evaluated tasks. Additionally, they compare their model with recent work on text descriptions of given motions and demonstrate that MotionGPT overperforms recent work. Section 4.3 Ablation Studies. In Section 4.3, we discuss several studies that further examine the details of our MotionGPT model. As a language model that understands and generates motion, MotionGPT uses T5 as its underlying structure. We train these models first with a general pre-training stage, followed by specific instruction tuning. The size of the model and the approach to training both play key roles in how well the MotionGPT performs. We put this to the test using various common motion tasks, with more thorough investigations detailed in the supplement materials. Looking first at the model sizes, we tested different sizes across 4 types of motion tasks. We compared the performance of models of 60 million, 220 million, and 770 million parameters, in addition to the original 220 million parameter MotionGPT. The results revealed that the base 220 million parameter model performed impressively, even when compared to the smaller 60 million parameter model. Interestingly, increasing the model size beyond the base did not lead to significant enhancements. In some cases, the larger models even performed worse, especially in tasks involving intermediate motion. We suspect this might be due to the limited size of current motion datasets. For instance, the human ML3D dataset consists of just 15,000 motion sequences, a number dwarfed by the billions of data points available in language and image data. Next, we evaluated the effect of our unique instruction tuning method on different model sizes. The results indicated that this technique improves the flexibility of MotionGPT, enabling it to handle more types of motion tasks, such as motion completion, and enhancing its performance on the text-to-motion task. However, we noticed a decrease in performance for tasks involving pure text generation, potentially because of the limited amount of text descriptions and their associated motions. In Section 5, we delve into a discussion about MotionGPT's strengths and weaknesses. To the best of our knowledge, this is the first attempt at using a language model to generate human motion. However, there are certain limitations to be aware of. MotionGPT is designed to work only with the motion of human bodies and doesn't consider other aspects like facial expressions, hand gestures, or even animal movement. Furthermore, our method does not account for interactions between multiple humans or between humans and objects or the environment. Despite these limitations, we believe MotionGPT holds significant potential for modeling human interactions within a motion language framework and generating controllable motions. We envision MotionGPT as a unified motion language model capable of producing believable human motion and descriptive language based on given prompts. In comparison to similar motion diffusion methods, MotionGPT competes favorably in tasks like motion generation, motion captioning, motion prediction, and intermediate motion tasks, all with the use of a single pre-trained generative model. As we continue to accumulate more language data and refine our models, MotionGPT will be able to handle tasks like natural question answering. Our extensive testing across various tasks related to human motion has shown the effectiveness and scalability of MotionGPT. Section Summary. The performance of MotionGPTs is influenced by both model size and training strategy. Model sizes were evaluated across 4 motion tasks, with the 220M base model achieving remarkable performance compared to the smaller 60M model. Instruction tuning enhances the versatility of MotionGPT, enabling more motion tasks like motion completion and improving the motion performance of the text-to-motion task, but for pure text generation tasks, the model performance is downgraded.